So, CHEM212, and we're going to use this sample exam that I handed out in class, and it's available in Brightspace. And we have several questions and structures to deal with, and mechanisms to deal with, recipes to deal with in these questions. And we're going to take them one at a time. And I'm pretty sure that, I've already done this in live class, but we lost our internet connection, so it's not recorded. That's why I have to come back and record it again right now. So there are several in here that don't make any sense to me, so I'm not going to expect my class to make any sense of them either, and I'll point them out when we get to them to discard those, and I'll make a note of it here as we proceed also. Okay, so this document covers Chapter 12 and Chapter 13 for Exam 3 in CHEM212. So question number 1, which of the following contains a nonpolar pi bond that is likely to participate in an electrophilic addition reaction? All right. The keys there are not just the pi bond, but the nonpolar pi bond. Notice that whenever you have a pi bond in which one of the members is more electronegative than the carbon, then you will have a polar pi bond. Now, reactions do occur with those types of pi bonds, but that's covered in a different chapter. And I'm not even sure we're going to get to that. No. Those are chapters that we skipped, right? There's just not enough time in the course to cover all those reactions. So those, if you're interested, then they are in the textbook, and you can go look at them. Let's see, we skipped from let's see, 9, 12. Actually, we're not going to even get to those chapters. Yeah, 13, 14, 15, 16, 17. They occur in Chapter 18 and beyond. So don't worry about those. Not for this test. Okay, so in order to have a nonpolar pi bond, you need equivalent atoms on either end of the pi bond. And for our purposes, those both have to be carbons. So the only example here of this Roman numeral 1 through 5, the only example here that has a nonpolar pi bond is Roman numeral 3. Right? The rest of them are polar pi bonds. Right? So that's why for number 1, the answer is C. Okay. Number 2, identify the 2 elementary steps in order in the following mechanism. All right. So what we see here is bromination of this carbon bond, and this occurs in what we learned in Chapter 12 of a strong Bronsted acid, how it is attacked by the pi bond, because the electrophile, let's see, the electrophile is hydrogen bromide, and the nucleophile is the electron-rich pi bond. So that pi bond attacks that hydrogen and forms a bond, right? Let's draw this one. We won't draw every one that we encounter, but if we do this one, we have this cyclohexene with a double bond here, and then we have the HBr like that. So we get this pi bond attacking that hydrogen, forming a bond with it, and then this bromine is the leaving group, and we get the bromine. Let's see, let's put it over here. We get this bromine ion like that, and we get this hydrogen bound here, and that gives us, in the first step, that gives us the hydrogen here and the carbocation there. Okay, so this first step is the electrophilic addition. Right, this electrophile here is added added to that pi bond. That's electrophilic addition is the first step. The second step is coordination, because now we're going to form a bond here. Remember, anytime you have a coordinate covalent bond, the electron pair to form the bond comes from only one side, one species. Right? Since this is a carbocation, it doesn't have any extra electrons. So both of the electrons come from the bromine. That's a coordination step. So electrophilic addition in step 1, coordination in step 2. All right. So what's the rate determining step in the following reaction? All right. We have this example, but we can use this one that's already on the board. The rate determining step, this is electrophilic addition. And then this step is coordination. Okay. The rate determining step is the slowest step. And the slowest step is the one that, look at it this way. What is the result? What are the products of each step? The product of this first step is a carbocation. The carbocation is very, very unstable. Right? We can stabilize it, so to speak, under certain circumstances, but it's very unstable, and the equilibrium tends to lie over here. So as we produce it at a very slow rate, then the coordination step is very fast. It happens quickly. So the rate determining step is the one that produces the least stable product, and that's the electrophilic addition. So in this process, electrophilic addition is the slow step, the rate determining step. Number 4, which of the following is unlikely to undergo an electrophilic addition reaction? Okay. We mentioned this in lecture. Electrophilic addition will only take place on a nonpolar pi bond, and incidentally, non-aromatic bond. All right. So we have aromatics here. We have number 2 is aromatic. We have number 1 is a nonpolar pi bond. Number 3 has an aromatic, but it also has a nonpolar pi bond. And so does 4, so does 5. Right? So the one that will not undergo electrophilic addition is this benzene ring. Okay, that's that simple. And it's primarily due to the fact that electrons are delocalized over the entire structure. They're not concentrated in that pi bond. Delocalized, which makes them non-electrophilic, so to speak. All right. What's the major product of the following reaction? Well, for this one, we want to look at, let's see, let's keep this centered. We want to look at this reaction in terms of, right, this one is an aromatic ring, so no reaction is going to occur there. But we have a double bond there, and we have HBr. Okay. Now, the question is, how does the hydrogen and the bromine, how do these two add to that? because we know that the first step is going to be an attack here on that hydrogen. And then that will leave, this is the electrophilic addition. And that will leave us with what species? Well, the question is, the hydrogen will add in a Markovnikov fashion. Right? So the hydrogen is going to add right here. And that will form a carbocation on this one. The reason it does that is that this carbocation is more stable than it would be if we made it there. If the hydrogen added here on that carbon, then we would have a primary carbocation, which is very, very unstable. A secondary carbocation is more stable. So the Markovnikov addition occurs in such a fashion that we get the more stable carbocation before the coordination step. And then, of course, that adds the bromine, right? So, excuse me. The consequence of that is to produce Roman numeral 3. That particular bromide, let's see. Well, that particular bromide, number 3, is the major product. Okay, number 6. Identify the reagent needed to carry out the following reaction. All right, if we're going to get well, first of all, when you have an alkene like this, right, if you just put it in water, there will be no reaction, right? The water is not a strong enough nucleophile to receive the attack from this electrophile. So what you need to do then is activate with a strong acid, right? In order to leave a hydroxyl on a carbon. And this addition occurs in Markovnikov fashion. In other words, we form, actually, this is acid catalyzed addition. Yeah. Okay. This acid catalyzed, what we need to do is activate the water molecule. In other words, this strong acid produces hydronium ions. So as long as we have the hydronium ions, then this attack will occur, and we want to put this hydrogen on this carbon right here, right? So this molecule is going to attack here, form a bond there. These electrons are going to go here, and that produces, that regenerates the water molecule. But now that we've done that, we've produced that hydrogen there and this carbocation. Now we can get the nucleophilic attack there, right? And that forms this molecule with a water attached to it, like that. Let's see, like that. And this is, let's see, This is still positively charged. Right? We didn't neutralize anything. So that's positively charged. And then we get a proton transfer. So this water molecule now attacks that proton, and then these electrons transfer down here, neutralize that carbocation with that positive charge, and leave us with the hydroxyl on the secondary carbon. So this acid catalysis is necessary to produce that hydronium ion, or nothing proceeds. You don't even get the first step. So you need water and strong acid. So the best answer here is C. All right. Okay, number 7. The electrophilic addition step in the reaction below can result in 3 carbocation intermediates. Rank these carbocation intermediates in order of increasing stability. All you have to know about the stability of a carbocation is tertiary is more stable than secondary, and secondary is more stable than primary. So 3 is more stable than 1, and 1 is more stable than 2. All right. So if you look at the way the arrangements are, 3 has a caret that makes it greater than 1, and 1 has a caret that makes it greater than 2. B is the answer. So pay attention to those carets. Stability is greater than. So the stability is greater than, 3 is greater than 1. That's the way you look at this answer. Number 8. Major product of the following reaction, you have HBr in excess. All right. So let me tweak my brain for a second. HBr in excess across an alkyne. All right. All right. What we're going to produce across this alkyne is a fully substituted, right? All the pi bonds are gone now. But where do the halogens reside? Well, in 2 steps. First, we produce a vanillic cation. In other words, a carbocation that still has one double bond left over. So if we use, let me go back. I can't see it from here. Okay, we're going to use 1, 2, 3, 4, 5. We're going to use this one. 1, 2, 3, 4, 5. There we go. And HBr in excess. So in typical fashion, HBr, we get pi bond attack here, and then bromine is released. Right? Okay, so we form a Markovnikov addition, electrophilic addition, where they put the hydrogen on this carbon, and we form a cation, a vanillic cation here, right here. And this hydrogen now is bound over here. Okay. And then this bromine attacks here. So that produces the, let's see. One, two, three, four, five. 1, 2, 3, 4, 5. That produces the bromine on this secondary carbon. And then we go through the coordination step, electrophilic addition, coordination, and then we do another electrophilic addition. in which the this pi attacks that one and puts another hydrogen out here and makes another carbocation there. Okay, so now this one, this ion now attacks that in an SN2 attack. And coordination step, excuse me, not an SN2, a coordination step, and forms the bond. Now, why do we still get a carbocation here? Well, we get a carbocation there because it's resonance stabilized. Well, in this case, it's not so much resonance stabilized as it's on a secondary carbon, right? That's a more stable carbocation. If we had a phenyl group out here, then we would get resonance stabilization. But in this case, we simply are on a secondary carbon. And that's why now this second bromine attacks that same carbon, and we get a geminal dihalide. Geminal meaning twins. So both these bromines are on the same carbon. That's a geminal dihalide or dibromide in this case. And that's why Roman numeral 1 is the preferred product. All right, number 9. Which statement best describes the driving force behind the electrophilic addition of strong acid to an alkene? This goes back to our discussion of bonds broken, bonds formed. If there's an energetic advantage, then the reaction is favorable. So if we look at just the double bond, right, on this side, and we have, for our example, our Bronsted acid, then what is broken here? We've broken one pi bond and one sigma bond. Okay? And in the end, we get a bromine here and a hydrogen there. So we formed a sigma and a sigma. Okay? Sigma bonds are stronger than pi bonds, which means, in chemical terms, it means that these are at lower energy. They're more stable. Stronger bonds are more stable. They're at lower energy. So the amount of energy required to break this bond is lower than it is for that one. So the stability is in the formation of two sigma bonds from a pi and a sigma. So which one of these statements satisfies that? The reaction is favorable, D, because the total bond strength in the products is greater than in the reactants. This bond strength, and remember how we determined bond strength. How much energy do you have to put in to break the bond? So if these are at lower energy, if sigma's at lower energy, you got to put more energy in to break it. Right? That's a stronger bond. Total bond strength, total bond energy. All right, number 10. Give the name of the specific functional group present in the following molecule. All right, we discussed that just a few minutes ago. This is the formation of a geminal dihalide. All right, that's the functional group, a dihalide, a geminal dihalide. Gemini means twin, right? So we have twins. We got chloride in this case attached to the same carbon, right? So they're considered twins. Geminal dihalide. Number 11. Draw the complete detailed mechanism for the following reaction and predict the product. All right. So if we have, well, let's do that. we have a cyclohexane here. Oops. All right. Cyclohexane there. And to it, we have fused, well, cyclohexene, we have fused a 5-membered ring. Like that. Okay? So we've got HBr. What's going to happen? Well, we get an electrophilic addition, the rate determining step, electrophilic addition when this pi bond attacks that hydrogen and releases that bromide ion. Okay? So, well, since this is a symmetrical molecule, then the hydrogen could add on this side or could add on that side. The carbocation is no more stable on one than the other. Right? So the coordination step will occur either a carbocation here or a carbocation here. So we've got like that. We have our hydrogen added here. I just chose that one. And then we attack here during the coordination step, and that produces this product, right? With a bromine here and a hydrogen there. Okay? That's the complete mechanism for this reaction and the predicted product. And it doesn't matter which side we attack, we get the same molecule. We can't tell the difference between one attack or the other. All right. Let's look at number 12. Okay, let's see. Out of position there. All right. What are the two possible major products for the reaction below? All right, so let's say we have that molecule and this one and this one and this one there. Starting material. Okay. If we have HCl, the pi bond will attack that hydrogen and will release the chloride ion. Okay. So we got that chloride ion released. Now, where does the carbocation reside? Well, there are two possibilities. Right? One possibility is we could form the in the electrophilic addition. We could get this product here. We could put our hydrogen there and our carbocation there. Or the other possibility is we could put the carbocation here and the hydrogen there, right, in the electrophilic addition. If this is the case, then the chloride ion will attack here, right? So then we get a product with chlorine there. But if we have this one, it's one carbon away from a tertiary carbon. And remember, we're only showing methyl groups here and attachments to the carbon, but there's a hydrogen in it. There's a hydrogen attached there. So if this hydrogen, if these electrons with the hydrogen go over here, we get a 1,2 hydride shift. And that puts the carbocation in a more stable position. Right? So this reaction then would put the chlorine on that carbon. And then now we got this one, and we got a chlorine there. So these are the two possible products. The major product, I think, would be this one because it gives you a more stable carbocation and will go faster. But you will get some of this. So since the problem asks you for two possible major products, right, then you've got this one and that one as possibilities. All right. 13. Let's see if I can clean this up a little better. Yeah, it's much better. Okay. All right. 13. Give an example of a compound containing a nonpolar pi bond that would be likely to participate in electrophilic addition reaction. In order to participate in an electrophilic addition, nonpolar pi bond, all you need is a non-aromatic alkene or a non-aromatic alkyne. That's it. Right? The sky's the limit. As long as they're non-aromatic alkene or alkyne, they can participate in electrophilic addition. 14. Fill in the missing starting material needed to complete the following reaction. All right. So if we're going to get a geminal dichloride, right, if we start with an alkene, we only get a single chloride on that secondary carbon because that's the more stable carbocation for the coordination step. So if we want two chlorines on that carbon, we need an alkyne. A terminal alkyne will give us that geminal dichloride. So you just draw 1, 2, 3, 4, 5. 2, 3, 4, 5. There. That's your starting material. All right. 15. Is a bit troublesome. We're asked to label the thermodynamic product and the kinetic product formed in the following reaction. Think back to when we discussed the difference between thermodynamic versus kinetic products. The kinetic product is the one that is energetically favored. In other words, if we look at our energy diagram, and we have, say, reactants here, and we go through a transition state, products over here, so reactants and products, then the one that produces the energetically favorable product is going to proceed by a kinetic mechanism, because once it goes over the hump, it gets to the other side, it's essentially a the right word. Irreversible. It's essentially irreversible. So the kinetic reaction is an irreversible reaction. That's why this usually takes place at low temperature. We would cool it down to, say, minus 80 degrees Celsius. The thermodynamic reaction is the one that is reversible. So even if it's the same product, it would be reversible if we increase the temperature so that we have enough energy to reach this activated complex step and go back the other way. So the thermodynamic one would be the one that is essentially reversible, right? So the more stable product is the one that is derived from the more stable or the faster produced and more stable carbocation, right? So the kinetic one is the one that produces the more stable carbocation, and that would be from, the origin would be from this one. Let's see, there, there. So we'd still have this one, and we'd have the carbocation formed here, and that would give us the brominated there. So the tertiary bromide would be the kinetic one. It's the more stable. It happens the fastest. Whereas by process of elimination, the thermodynamic one would be the less stable one, and more likely would be at a higher energy state because it's more unstable, right? And that one would give us, let's see, would give us this product, because we would be working from a we would be working from a primary carbocation. So the more unstable one is the one that is that's not exactly right. The more alkyl substituted one is thermodynamic. More alkyl substituted. Well, what we've got is a resonant structure here. That's why the double bond moved over from here to here. That's probably a hydride, not a hydride, a hydride. Yeah, I don't see any methyl movements in there, so that would have to be a hydride shift to move the double bond. But the thermodynamic one is the more unstable, the one formed from the more unstable carbocation. All right, number 16. Step one of erase. Hey, what? You do some maintenance on my board. See if that helps some. Sure, it's still centered. All right. Number 16. Briefly explain why the following hypothetical reaction does not occur. All right. This is one of those where we're trying to conduct an electrophilic addition using just pure water. The problem here is with the first step, right? The electrophilic addition step is the slow step, and water, the electrophilic attack from the pi bond is unfavorable. Why? Because of the product that it would produce, right? If we look at it this way, we have this cyclo, we have this hexene, and if we have water here, and we try to attack that hydrogen, what would that produce? That would produce a hydroxyl, right? That would produce a hydroxyl. The hydroxyl is very poorly stabilized negative charge. In other words, This is extremely powerful nucleophile. It's a powerful base as well. So anywhere it can find a hydrogen, it's going to take it, right? It could take it from another water molecule, or it could go back in here. And if we form this, well, this is our proposed intermediate carbocation, right? We have a hydrogen here and a carbocation there, right? So what is it going to do? It's looking for hydrogens, right? It's not looking for positive charges. It's looking for that hydrogen. And it would just go back in here and take that hydrogen, right? And it's a wash. The reaction won't occur, right? It looks like it doesn't occur because it goes backwards. This is very unstable, right? So the first step of this hypothetical mechanism is too unfavorable to occur because it would produce hydroxide, which has a poorly stabilized negative charge. Right? That's the magic statement right there. How about 17? All right. Give an example of a compound containing a nonpolar pi bond that would be unlikely to participate in electrophilic addition reaction. All right. We've looked at something like this before. Any aromatic compound contains nonpolar pi bonds, but is unlikely to participate in an electrophilic addition reaction because of the electrons in the pi bonds are not localized to any two-carbon system. In other words, those pi bonds are distributed over the structure. That's one of the definitions of aromatic compounds. Delocalized, excuse me. The electron density is delocalized over the entire structure, which means it's less electrophilic. Well, actually, not electrophilic. Right? It'd be less nucleophilic. Right? Extra electrons means nucleophilic. But the delocalization decreases the excess electron density of any of those two carbon-carbon bonds in that structure. So an aromatic compound contains nonpolar pi bonds, but is unlikely to participate in an electrophilic addition reaction. All right, number 18. I didn't put a highlighted answer to this one because it's very simple. Label the electron-rich and electron-poor species in the following elementary step and draw arrows to complete the mechanism. All right, so if we have that and this is electron rich. This is electron poor. And that pi bond attacks this hydrogen. We release that bromine, and that gives us the products. Okay? Very simple. Okay. Number 19. For the following reaction, draw the structure of the product and the mechanism by which it forms. Okay, so if we have this cyclopentene, all right, here we go, and it's got an isopropyl side group attached to it. Then we have this reaction, the electrophilic addition step is going to attack that hydrogen, then these electrons go here, Now we've produced the chloride ion. Now, what forms here? Right? The more stable carbocation is going to be right here. Right? So our hydrogen is added to this side. That's the Markovnikov, right? The more hydrogen substituted carbon gets the next hydrogen here. And then this is going to attack that carbocation and form the bond, the coordination step. So our product is going to have hydrogen here, have a chloride there. That's why this representation of the molecule is the correct one. All right. Okay, when a carbene reacts with an alkene, what functionality is created? When a carbene reacts with an alkene, we're just going to draw the double bond. So a carbene is simply a carbon with an electron pair, and it's sp2 hybridized. So the simplest version of a carbene, right? There are several types of carbenes, but the simplest one is this one. Right? So we have these two hydrogens, and we have that lone pair. Okay? So what happens is we attack that one, and this one comes down here. So we form a cyclopropane ring. This step in the reaction produces the cyclopropane ring. Right? What's the major product of the following reaction? All right. So if we have, we've got molecular bromide is going to be added to the alkene. And the alkene is coming in here with, let's see, well, there's more of it over here. But we've got a terminal alkene, and then the bromine is in here like this. Right? And I described in the lecture video that as this bromine approaches that these pi electrons, they induce a now I know how Joe Biden feels. They induce polarity. Pardon me. So as they approach, say this approaches first, this is going to be slightly positive, this is going to be slightly negative because the electrons repel one another. So this produces the positive side. Now we have an electron poor side, an electron rich side. So this one attacks that one. This one is released, and we form the bromonium ion. Okay. So when that happens, now this the other bromine, the bromide ion that's released here, now it attacks from the other side. This bond breaks, and we put bromine on one carbon and a bromine on the other carbon. Now, this doesn't properly show the stereochemistry, right? Because the bromine attack here comes from the opposite side. So this doesn't represent stereochemistry. But it's the best answer out of the ones we're given. Number one. All right. What starting material is required to complete the following transformation? All right, we've got oxymercuration with yes, oxymercuration. And then hydration. Okay, let's pause for a second here. I gotta check something out. This is in chapter 13. All right. That's oh. Okay. Notice that the product here, if we're going to use an oxymercuration, then we're going to end up creating an enol. That's the first step is going to produce this. Let's see. Is going to produce this enol like that, but it tautomerizes into the ketone, which is more stable. So our starting material then would be here, there, would be that alkyne. That alkyne would give us this ketone. All right, 23. Major organic product from the following reaction. All right, what have we got here? What we have is a diazomethane. Diazomethane. Yes. Diazomethane. And diazomethane, actually, let me do it this way. Because we're bound to there like that and like this. And if we shine light, H nu means light energy. So if we shine light on that bond, it's very weak. It breaks that bond and produces nitrogen gas, right? And it also gives us this carbene, right? Let's see, 1, 2, 3, 4. Yeah. it gives us this carbene, right? So it's got a lone pair of electrons, and it's less than an octet. Okay, it has a formal charge of 0, but it's less than an octet, so it's very reactive. And when it reacts with this alkene, it forms the cyclopropane ring, right? So 3 is your answer. This carbene that's formed in situ, carbenes have to be formed during the reaction, right? They're not stable enough to form and keep in a bottle. So it bridges across these two terminal carbons and forms this cyclopropane ring. All right, so number 3 is the correct answer. All right. How about number 24? What functional group will be formed in the following reaction? All right, so we have a this reaction with the borane, followed by a reduction step, follows anti-Markovnikov addition. In other words, instead of putting the hydroxyl group on the second carbon, the more stable carbon, it adds to the terminal carbon. So when it does that, and then we, let's see, hydroboration, oxidation, if we do the oxidation step, right, with hydrogen peroxide in basic solution, then we get an aldehyde. So we're going to form an aldehyde here on the end. It forms an enol, right? But the enol tautomerizes into an aldehyde. All right, what's the major product for this reaction? Let's see, oxymercuration of an alkyne. Okay. So it doesn't have to be reduced further, right? Not with alkynes. Alkynes automatically reduce themselves. This follows the Markovnikov addition, and that puts the hydroxyl on the second carbon, right? And that forms an enol with the second carbon, and it tautomerizes into a ketone. So we're looking for a ketone, and the only ketone I see is number 2, Roman numeral 2. Major organic product from the following reaction? All right. If we have excess bromine, then we're going to get bromination on both carbons, and both pi bonds will be gone. So number 5 is the best answer. We get 2 bromines on the terminal carbon. We get 2 bromines on the second carbon. And there's your answer. 27. Which of the following is true regarding the hydroboration oxidation of an alkene? Hydroboration of an alkene. One thing that borane does is it forms bonds with 3 alkenes. So 3 moles of alkenes are going to attach with the boron. So 1 mole of BH3 will react with 3 moles of alkene. We can look at these others. Hydrogen and an hydroxyl add with Markovnikov regiochemistry. Actually, it's anti-Markovnikov. C, the oxidation step is acid catalyzed. No, it's basic catalyzed. Hydroboration is stereospecific with hydrogen and BH2 adding in anti-fashion. Actually, they add in syn fashion, right? Because it's a concerted reaction. Right? If we have this double bond, then we form like that, like that. So it occurs on the same side, right? Not in anti-fashion, but in syn fashion. And so D is false. E, BH2 will add to the carbon with the greater number of alkyl groups. Actually, it adds to the carbon with the fewer number of alkyl groups. That's why it's anti-Markovnikov. All right, so the only one that works is B. B is the only correct answer. All right, this is one that I'm going to throw out. If you go back to your textbook, let's see, let me highlight this one as thrown out. If you go back to your textbook, you see that an electrophilic addition is followed by a 1,2 alkyl shift, right? The mechanism that's given in the text, I don't see an alkyl shift. It may be there, but that mechanism as presented in the book doesn't show it. I don't see it there, right? So I can't figure it out, so I'm not going to expect you to figure it out. What reagent best completes the following reaction? All right, we want to end up with, oh, this is a bad one too. And here's why. Let's see. Let me check on this one. Okay, pause for a second. I'm gonna go to an unshared screen and see if I can figure this one out. Because the problem is, this puts an, look, there's an oxygen right there. But here, it's a carbon. So how do we change an oxygen to a carbon to an oxygen, right, in that step? The answer the authors give is A. Diacetyl borane and then oxidation. So diacetyl borane. So let me go look at, pause for a second. Let me go look at my textbook. Hydroboration. Right. Yeah. That's an error. Right. There should be, let's see, diacetyl borane. 1, 2, 3 carbons. 1, 2. Oh, wait a minute. No, that's correct. No, that's my mistake. This is a valid question. Right? Let me, let's see. There. Okay. My mistake. I didn't count carbons. All right. If we count carbons, there's one, let's see, over here we got 1, 2, 3. 3 carbons off of that cyclohexane. 1, 2, 3, still got 3 carbons, and then we have the aldehyde. So that's valid. And this hydroboration with oxidation step will give you that one. This produces the aldehyde rather than the ketone. If we used B2H6 and THF, we would get the ketone. But in this case, we want the anti-Markovnikov. So yeah, that's a valid step. All right. Carbenes react with alkenes by using which fundamental step? Electrophilic addition. Right. This is what we've been studying in both chapter 12 and 13. We get an electrophilic addition using a carbene. What's the major organic product of the following reaction? All right. Here, we're trying to add one equivalent of bromine on either a double or a triple bond. Now, the question is, which one of these is more reactive? Is the alkene part more reactive or the alkyne more reactive? Well, let's see. We're in an aprotic solvent with one equivalent of bromine. So one equivalent should give us, if it reacts with the alkene, we're going to get a dibromide. If it reacted with the alkyne, then we would get a geminal dibromide. And I don't see that. I don't see that here. Yeah. So we have to eliminate the possibility of reaction with the alkyne because it's not shown. And the only one that's shown is Roman numeral 3 that does give us a dibromide. So that's my only logic. It's not to say that the alkyne is not reactive. It's just that we're not given a choice, the proper choice for presenting that. It also says the major organic product. Right, the major organic product. Right, this is not a really solid question for me. I'm not going to throw it out, but it's not the best question I've seen. 32. Which reaction conditions would be unreactive on the substrate below? Well, obviously, I go straight to water. Right? You put an alkene in water and nothing happens. 33. What intermediate could be found in the mechanism for the following reaction below? So an intermediate would be, if we're using an oxymercuric addition, and oxymercuration reduction. Oxymercuration reduction. Then we have to form a three-membered ring with the mercury. Right? Do we have any of those? Right? The only one that gives us a three-membered ring as an intermediate product in the mechanism is Roman numeral 2. What's the most likely product for the reaction below? Okay, this is the one where I always forget my terminology. We're hydrogenating an alkyne, and we're using a Lindar catalyst, which is a poisoned catalyst, which means we are limiting the reaction to only partial hydrogenation. Okay? And the hydrogenation is going to be a syn addition. Right? So we need to have a double bond left over with a Z configuration, right? And the only one that I see with a Z configuration, well, actually there are two of them. Roman numeral 2 and Roman numeral 4 have Z configurations, but Roman numeral 4 has a Z configuration on the wrong carbons. Right? Notice that the starting material has a 2-3 carbon-carbon pi bond. And 4 has a 1-2-3-4, right? So can't be 4. So Roman numeral 2 is the only possible answer. How about number 35? What mechanistic step can be found in the reaction below? So we're doing an oxymercuration followed by a reduction. And the first step is electrophilic addition with the formation of a three-membered ring. Right? So do we have an electrophilic addition? No, we don't. There's no electrophilic addition in there. Second step is going to be an SN2 substitution, nucleophilic substitution. Right? So that's the only possibility. We don't have any other options. What's the major organic product for the following reaction? Okay, notice that we have D and D here. That's deuterium. Right? So when we hydrogenate this molecule, we're going to add hydrogens across that double bond. And they're going to be added in a syn fashion. But which side are they going to add on? Notice that the adsorption of the pi carbons is going to be on the side opposite the steric mess, right? So if we have a 1, 2, 3, 4, 5, we have a this, and then we have this and that, right? So how can this molecule approach the catalyst? It can't approach it from this side because of all that steric hindrance. It has to approach it from this side, which means the hydrogens are going to be added on this side of the molecule, right? The hydrogens are always added syn, but which side is syn, right? We could add them on this side, or we could add them on the top side, which would be Roman numeral 3, right? But in that way, the molecule would have to be flipped over, and it won't happen because of all this steric hindrance. So it has to be added, the hydrogens have to be added down here. Like that, with the deuteriums up here. Okay? Roman numeral 1, A, is the answer. Which of the following is not part of the mechanism for the catalytic hydrogenation of the alkene? Well, A, B, C, and E are steps in the catalytic hydrogenation of an alkene. D is not considered a step simply because of our definition. A proton transfer actually has a movement of a proton from one molecule to the other. In this case, we're not moving a hydrogen from one molecule to another. We're forming a bond between free hydrogens on the catalyst and a carbon that was once part of an alkene. Right, so it's not technically a proton transfer from metal to carbon. So D is the one that's not there. Let's see, 38. What's the major organic product from the following reaction? We got bromine excess, right? So we're going to put 2 bromines on one on the primary carbon and 2 bromines on the secondary carbon of that alkyne. As long as we got bromine in excess, then we're going to brominate both those carbons to the maximum. What's the formal charge on a carbon in a carbene? It's 0. Right? The formal charge is 0. Draw the alkene that can be epoxidized using MCPBA, which is metachloro benzoic acid, to yield the following. Right? The oxygen adds, we preserve the stereochemistry. So the starting material then would be this phenyl group. And then we would have, let's see, would be consistent here. Well, they wrote it in. You don't have to write it in, but we're going to just for kicks. All right, so if we're going to epoxidize, form an epoxide here, right? That means these have to be on the same side of the molecule. Right? Right. So we have to have the methyl group and the phenyl group in a Z configuration, the same side. All right. What starting material best completes the transformations below? All right. If we want to form an aldehyde, and we've got a borane, which is subsequently oxidized with hydrogen peroxide, then this is going to be an anti-Markovnikov addition. That means we need a terminal alkyne. So all you have to do is change the last 2 carbons to an alkyne, drop that oxygen off of there, and change that to an alkyne, and that will be your starting material. What reagent is required to complete the following reaction? All right. The giveaway for this one is the H-nu, the energy, light energy. Right? We're forming a carbene from diazomethane. So diazomethane would be the material that is exposed to this light to produce the carbene that forms the cyclopropane ring. Right, so diazomethane is the missing material. Right, so the reagents that are best suited to complete the following reaction. Right, we need an anti-Markovnikov addition. So that means the hydroxyl would have to be on the terminal carbon. Normally, hydroxyl would be on the secondary carbon. But anti-Markovnikov can be produced by hydroboration followed by oxidation. So we put BH3 with stabilized with tetrahydrofuran as the first step, followed by oxidation with hydrogen peroxide in basic solution. Number 44. Supply the reagents that are best suited to complete the following reaction. All right. MCPBA could attack from either side of the alkene, the double bond. If attacked from one side, it's going to produce the product on the left. If it attacks from the other side, it's going to produce the product on the right. It forms the epoxide. So MCPBA would be your reactant. All right. What's the major organic product for the following reaction? Well, let's see. If we have this molecule like that, and we have a bromine, right? So bromine is going to like this, and this, and this. It's going to attack that one. This one will be released as the bromide ion. And we form a bromonium ion. Like that. Okay? All right. If that's the case, then which bond is the weakest? The weakest bond is this one. This is the more positive one. And this is the less positive one. So this bromine is going to attack there. And that would give us, let's see, the carbon, and it's going to give us a bromine here and a bromine here. Right. So actually, this second one is the better selection. That one is probably not the best one. So let me say, let's see, let's remove that highlight. No color. There we go. The major product is going to be this one. Yeah. In fact, I probably shouldn't have even put that one up there. The major product is going to be this one right here. All right, 46. What reagents are best suited to complete the following reaction? All right, we've got an alkyne, and we want to form a ketone. So oxymercuration with reduction would give you the Markovnikov addition. Yeah, it would put the hydroxyl on the secondary carbon, which would form an enol that would tautomerize to the ketone. So oxymercuration reduction would give you, and you can write the reagents in, or you can just say oxymercuration reduction. We know what that means. A carbon atom that possesses two bonds and a lone pair of electrons is called a carbene. Right? 48. What's the major organic product for the following reaction? All right. So we're forming a carbene, and it's going to put a cyclopropane on that secondary carbon, right? Just as shown here. It's simple. Just forms the three-membered ring. Following alkene is treated with Br2. What's the stereochemical relationship of the two bromine atoms in the product? They're anti, right? Right. One bromine is added to make the bromonium ion, and then the bromide ion has to attack the other side. Right. So they form, the stereochemistry is anti. Draw the structure for the major organic product for the following reaction. All right. This is going to give us a this particular reaction, this oxymercuration reduction. gives you the Markovnikov addition. So the hydrogens are going to be added to the primary carbon. Hydroxyl is added to the secondary carbon. So there's your structure. What starting material gives this one, right? We've got bromine here. We got bromines everywhere. We had to start off with an alkyne. The alkyne then would have been on these two terminal carbons, right? The primary carbon and the secondary carbon would have been the alkyne, and complete bromination of those two carbons will give this product. If you use a Lindar catalyst, however, a poison catalyst, then you only get the Z isomer of the alkene left over after you hydrogenate. So that's why across that triple bond, we're going to leave an alkene behind, but the constituents, the substituents, have to be Z isomers to one another, because the hydrogen adds in syn fashion on one side, and that means everything else has to be on the other side. So I've drawn the structure there to show you what it looks like. Predict the major product of the following reaction. I don't think there is a product. Right? There are no nonpolar carbon alkenes or alkynes. Are we going to hydrogenate the oxygen, or are we going to hydrogenate the cyanide, the cyano group? Well, we haven't learned that yet. Right? Is it going to happen? I suppose it could, but I don't see how. Right? So there's no product from this reaction, in my mind. That's the answer I would accept. There is no product. And that's it.